You have been told your whole life that mass creates gravity. Objects with mass attract each other, and the more mass you have, the stronger the pull. Newton told us that, and it seemed perfectly fine for a few hundred years. An apple falls from a tree, the moon orbits the earth orbits the sun. All of it fits the formula. But here is the thing that should bother you, and it never gets talked about enough. Newton himself admitted he had no idea why it worked. He could calculate gravity with extraordinary precision. He just could not tell you what gravity actually is. He called it action at a distance, which is just a fancy way of saying something is happening, and I do not know how. Two objects separated by empty space somehow reach across that void and pull on each other without touching, without wires, without any visible mechanism whatsoever. And for a long time, physicists just accepted that. They had the math, and the math worked, so they moved on. Then along came Einstein, and he looked at this whole picture and said, "Wait a minute, you are asking the wrong question entirely. The question is not how does mass reach across space to pull on things. The question is what is space itself actually doing when mass is sitting in it." Let me try to build up to this carefully, because it is one of those ideas where if you rush it, you miss the whole beautiful thing. Imagine you have a flat rubber sheet, stretched out tight and horizontal. Now you place a heavy bowling ball in the center of that sheet. What happens? The sheet curves downward around the ball. It sags. Now roll a marble across that sheet. The marble does not travel in a straight line anymore. It curves toward the bowling ball. Not because the bowling ball is grabbing the marble. Not because there is some invisible force reaching out. But simply because the geometry of the sheet has been warped, and the marble is just following the natural path available to it on that curved surface. This is more or less what Einstein figured out about the universe, except instead of a two-dimensional rubber sheet, we are talking about four-dimensional spacetime. And instead of a bowling ball causing a sag, we have mass causing a curvature in the very fabric of space and time. Gravity is not a force in the traditional sense at all. It is the result of curved geometry. Things fall not because they are being pulled, but because they are following the straightest possible path through a space that has been bent. Now, this sounds like a metaphor, like a teaching trick, but it is not a metaphor. The mathematics of general relativity describes exactly how much curvature a given amount of mass produces in the spacetime around it. The equations are real, they are precise, and they have been tested to extraordinary accuracy. The bending of light around the sun, the precise timing corrections required for GPS satellites, the detection of gravitational waves from merging black holes, all of it confirming that spacetime actually curves, that mass genuinely warps the geometry of the universe. But you might still be sitting there asking the deeper question, fine, mass curves spacetime, but why? What is the actual mechanism? What is it about matter that causes this warping? And here I want to be completely honest with you, the way I always try to be. We do not fully know. We know the relationship between mass energy and spacetime curvature with high precision. Einstein gave us the field equations, 10 interlocked equations that describe this relationship beautifully. But why matter curves spacetime? In the same deep mechanical sense that Newton could not explain why mass attracted mass. That question is still open at the deepest level. What we can say is something genuinely profound, though. In the framework of general relativity, mass is not special because it produces some magical pulling force. Mass is special because it contains energy, and energy is what is actually doing the work. Einstein showed us that mass and energy are the same thing expressed differently. That famous relationship, mass equals energy divided by the speed of light squared, rearranged to energy equals mass times the speed of light squared, tells you that sitting inside every bit of matter is an enormous concentration of energy. A small amount of mass is equivalent to a gigantic amount of energy, and it turns out it is energy, or more precisely energy density and momentum and pressure, that curve spacetime. Mass is just the most obvious and stable form that energy takes in everyday matter. So when you have a planet sitting there, what you really have is a very large concentration of bound-up energy, electrons and protons and neutrons all held together in atoms, all vibrating, all containing the energy of their mass, all held in place by the forces within matter. And all of that energy, that enormous density of concentrated energy, curves the spacetime around it. The Earth curves the spacetime in its neighborhood. You are not being pulled down to the floor right now. You are in a region of curved spacetime, and the natural path through that curved spacetime happens to be downward toward the center of the Earth, and you are following that path. Here is another way to think about it that I find compelling. In curved spacetime, time itself runs at different rates depending on where you are. Time runs slightly slower near a massive object than it does far away. Clocks on the surface of the Earth run a tiny bit slower than clocks at high altitude. This has been measured. It is real. And here is what is remarkable about this. Objects moving through spacetime always take the path that maximizes their own experience time. They always move in the direction where time runs fastest for them. And near a massive object, that direction is toward the mass. Moving toward the Earth actually puts you in a path where the geometry allows more time to flow for you. Gravity, in a sense, is matter following the natural bookkeeping of time in a curved universe. Now let us go one layer deeper, because there is a concept in general relativity called the geodesic, and it is central to all of this. A geodesic is the straightest possible line through a curved space. On a flat table, the straightest line between 2 points is what you would draw with a ruler. But on the surface of the Earth, the straightest line between 2 cities curves along the surface of the globe. Pilots know this. They fly great circle routes, which look curved on a flat map, but are genuinely the shortest paths on the curved surface. In spacetime, everything travels along geodesics. Planets orbiting the Sun are not being tugged into curves by some force. They are traveling the straightest possible paths through spacetime that has been curved by the Sun. Their orbits are geodesics in curved spacetime. There is no force making them curve. They are going straight, in the fullest geometric sense, through a universe whose geometry is not flat. This reframing changes something important about how you think about the problem. In Newton's picture, gravity is a force that acts on things and changes their natural straight-line motion. In Einstein's picture, gravity is not changing anyone's natural motion. Everything is always doing exactly what a free object does, following a geodesic, traveling the straightest path. The mass of the Sun just changes what straight means in that region of the universe. Now, there is a third piece to this story, and it comes from quantum mechanics, and it is genuinely unsettled. We have 2 extraordinarily successful theories of physics. General relativity, which describes gravity and the large-scale structure of spacetime, and quantum field theory, which describes everything else, the electromagnetic force, the weak nuclear force, the strong nuclear force. Every other fundamental force we know about has been successfully described in the quantum framework. Quantum electrodynamics tells you exactly how charged particles exchange photons and produce electric and magnetic forces. The strong force has gluons. The weak force has W and Z bosons. All of these forces are mediated by particles, by little packages of energy that carry the force from one place to another. For gravity, the theoretical prediction is a particle called the graviton. A graviton would be a massless particle traveling at the speed of light that mediates the gravitational interaction the same way photons mediate the electromagnetic interaction. The math suggests it should have a spin of 2, which distinguishes it from photons with spin 1. But here is the honest truth. We have never detected a graviton, not once. And the theoretical attempts to incorporate gravity into quantum field theory the same way we incorporated electromagnetism have all run into severe mathematical problems. The equations produce infinities that cannot be cancelled out using the standard tricks that work so well for the other forces. This is the problem of quantum gravity, and it is one of the deepest unsolved problems in all of physics. String theory is one attempt to solve it. Loop quantum gravity is another. Neither has been experimentally confirmed. So while we have a beautiful and highly accurate classical description of why mass curves spacetime, the deeper quantum mechanical picture of what is actually happening at the smallest scales, what is actually transmitting the gravitational interaction, remains genuinely unknown. Let me tell you what I find most interesting about all of this from a purely physical standpoint. The fact that gravity is so much weaker than the other forces is itself a deep mystery. Electromagnetism is roughly 10 to the power of 36 times stronger than gravity. Think about that. A small refrigerator magnet can hold a paperclip against the gravitational pull of an entire planet. If you had 2 electrons, the electromagnetic repulsion between them is about 42 orders of magnitude stronger than the gravitational attraction. 42 orders of magnitude is an almost incomprehensible difference in scale. If gravity were even slightly stronger than it is, the universe would have collapsed back in on itself almost immediately after the Big Bang, before any stars or planets could form. If it were slightly weaker, matter would never have clumped together into anything interesting. The particular weakness of gravity, that enormous gap between its strength and the strength of every other force, has no explanation in current physics. Some theoretical frameworks attempt to explain it by proposing that gravity bleeds off into extra spatial dimensions that the other forces cannot access, making it appear weak in our observable 3 spatial dimensions. But again, this is speculation without experimental confirmation. What we are left with, honestly, is this. We know that mass creates gravity because mass contains energy, and energy curves spacetime, and curved spacetime changes the paths available to other objects moving through it. We can calculate this with incredible precision. We can use it to navigate space, to predict eclipses, to detect gravitational waves from collisions a billion light-years away. But the deepest why, the quantum mechanical story of what is actually happening at the Planck scale, where spacetime itself might be grainy and discrete, that story is still being worked out. The equations that would unite general relativity with quantum mechanics have not been found yet. And I think there is something genuinely exciting about that. We are not at the end of the story of gravity. We are somewhere in the middle. Newton figured out the math. Einstein figured out the geometry. The next chapter, the quantum chapter, is the one the physicists alive today and in the generations after us are going to write. The question of why mass curves spacetime at the quantum level, what is actually being exchanged, what spacetime is made of at the smallest scales, those are the questions sitting at the frontier right now. And the fact that we do not know the answer yet is not a failure. It is an invitation. The most exciting phrase in science is not "I have found it." It is that it's funny. And right now, gravity is very funny.